let's apply the derivative to a specific function. Y equals ax cubed equals, let's say, 0.002x cubed, the quantity that we got when we did our model just a little while ago, a model for the sand pile volume versus diameter. So remember that y refers to the volume of a sand pile, x to the diameter. The derivative of this function, y prime of x, is 3ax squared. Since a is 0.002, we get 3 times 0.002x squared, 0.006x squared. Now you see some scribbling here about rises and runs and y primes and so forth. The question that we're going to pose is, between depth 15 and depth 15.25, I'm sorry, between diameter 15 and 15.25, how much difference is there in the volume? Well, we could, since we have the function, plug 15 into this function and see what the depth is, then 15.25 and see what the, not the depth, thinking depth versus time, plug in 15 and see what the volume is, 15.25 and see what the volume is, and subtract them. That would be a very easy way to find the rise of this slope triangle. However, we're going to look at it in a slightly different way. Okay? Now let's just frame the problem here and make sure we understand the problem. Okay? Y prime is this. And we're going to use the y prime to predict what the rise ought to be here. And we'll see how that works in a minute. I'll outline the idea, but let's pose the problem. So if y prime equals 0.006x squared is the rate of volume change, WRT stands for with respect to diameter x, because remember, we've got volume versus diameter, so that we're talking about a volume change on the vertical divided by a diameter change in the horizontal, and we call that rate of volume change with respect to diameter. There's no time involved in this. The question is, how much volume change do we expect at diameter 15 to increase the diameter to 15.25? In other words, how much sand or sugar do we have to add? Just a brief sketch of how we're going to solve this using the rate function. It's fairly simple. The rate at diameter 15, I almost said clock time, but the rate at diameter 15 we get to be 1.35. If we plug in 15 for x, square that, we get 225. And then multiply that by 0.002, we get 1.35. So you might think 1.35, if we're doing tablespoons of volume, then tablespoons per centimeter, if this is measured in centimeters. It's not, but if it was, that's how it would be, tablespoons per centimeter. That is the slope of the graph at this point here. That's not the average slope between here and here. However, the slope at this point, the instantaneous slope, the slope of the tangent line at this point, is going to be reasonably close to the slope of this slope triangle here. And of course, if the slope triangle is very small, it's going to be very close to the slope, because of course we get the slope of the tangent line by taking the limit as this triangle shrinks down to a point here. And 0.25 is not nearly as big as it looks on this graph. I had to exaggerate the scale. 0.25, if this is 15, 0.25 is just going to be right next to it, almost right on top of the same point. So we're talking about a very small interval here.